Welcome to the presentation video for the Additive Manufacturing course. Our team has decided on creating the OPRA, the one-part rocket assembly. This presentation will cover our proposed business plan. Cryogenic thruster design is an optimized thruster design that aims in providing safe and reliable thrust for a variety of spacecraft. Liquid hydrogen is the fuel of choice due to its weight, high burning intensity, and that it must exist at roughly 20 Kelvin in order to be in a liquid state. Propellant is then burned in the gas generator and sent through the combustion chamber to provide the required thrust. As in most cryogenic rocket engines, some of the fuel in the gas generator cycle may be used to cool the nozzle and the combustion chamber. This is known as regenerative cooling. Liquid hydrogen is cold enough to reduce the heat on the nozzle surfaces, and therefore, for the various adaptations, this type of design is used by companies like NASA and SpaceX. Heat from combustion and large skin friction combined creates this high temperature environment that the nozzle must survive in. The current products in the market include the SpaceX Raptor, the SpaceX Merlin, and the Rocketdyne F1. They all come in varying sizes and therefore also varying prices, where the Raptor is $2 million, the Merlin is $1 million, and the Rocketdyne F1 is $30 million. The general construction of the SpaceX Raptor is based on the outer surface being created of Inconel alloy 718, a structural sandwich of nickel and copper, and an inner surface made of a state-of-the-art alloy that is currently used for fabricating rocket engine combustion liners. The reason it is made this way is because when ignited, the pressure difference between the cooling channel and the inner wall is approximately 20 megapascals, which is about 200 times the atmospheric pressure. Therefore, it must be constructed to withstand it. The target consumers tend to be space corporations and programs, and the only consumers interested are highly specialized and would require this highly specialized piece of equipment. The demand is rapidly growing with space being an open market. Many companies and countries are developing rockets as well as systems to deliver payloads to the International Space Station. This means a variety of thruster sizes and outputs are also evolving. Later on in the presentation, we will discuss how companies like Velo3D and Betatype are starting to experiment with creating small-scale thrusters. They're having varying success, but it has yet to hit the open market as it is mostly experimental. There are currently two manufacturing methods used to create these nozzles. Method 1 is done by creating a structure by bending 8286 stainless steel tubes to the appropriate shape, surrounding these tubes with an outer layer of Inconel 718, and then brazing is performed in a custom chamber under a cover of hydrogen gas. Method 2 uses Inconel 600 tubes of a square cross-section wrapped in a spiral pattern. These tubes are then connected using a gas tungsten fillet weld. And finally, the upgraded design is done by constructing a sandwich with an inner liner of that super alloy. Brazing introduced the issue of varying thermal expansion that, if done incorrectly, introduced residual stresses causing cracks to form and propagate. The second method doesn't have to deal with the thermal expansion as much, however, more expensive process as each tube requires welding, which will significantly increase the labor costs. Additive manufacturing allows us to increase the complexity of the internal channels while keeping costs relatively low. The internal channels have a very complex inner shape that would increase the surface area that the cooling hydrogen would flow through, thus encouraging more heat transfer and maintaining a cool and safe nozzle. Scalability is also a large benefit of additive manufacturing, as we can use the same design and be able to print it in various sizes, thus expanding market opportunities. And finally, the uniform materials also aid in avoiding thermal expansion issues. The redesigned product will be utilizing a de Laval nozzle to achieve flow speed greater than Mach 1. Internal cooling channels help provide better cooling, and we can say that the typical size of our thrusters will be about the size of a door, or roughly 7 feet tall. As flow passes through the converging-diverging nozzle, flow will exit at supersonic flow, and this product will allow for higher temperatures, meaning smaller nozzles can achieve similar thrust. Additive manufacturing allows us to add cooling vanes with internal rather than external channels, and this means that the cooling is happening closer to the heat source, meaning we can therefore achieve those higher temperatures. Our design lets us utilize ceramics, where the old products were limited to metals. If they did use ceramics, they would be forced to simple geometries, whereas we are able to create more complex geometries. For our material selection, we have decided on using zirconium carbide. Zirconium carbide allows us to achieve temperatures higher than tungsten carbide or niobium, which is what's currently used on Merlin engines. Another advantage of using a single material is that we do not have the problems with thermal expansion in the components, as everything will be uniform. The additive manufacturing process we have selected is binder jetting. The reason this process was chosen is due to the materials is capable of printing and being able to work in high temperature environments, in our case zirconium carbide. It is able to create relatively complex geometry as every layer is supported by the powder bed. Advantages include good mechanical properties after it's been post-processed. The machine consists of standard components, meaning it's easier to upgrade, or in our case, it will be easy to make a custom machine. Higher speed than normal compared to material jetting, as only a fraction of the materials being actually dispersed. There's no thermal energy required, meaning there's no warping or not having to worry about bed adhesion as much. And the excess powder is going to be reusable. Disadvantages include a poor surface finish, as it tends to be quite rough due to the powder. The green body tends to have extremely poor mechanical properties, making post-processing a very necessary step. And it's not as common, therefore it can initially be more expensive. The closest machine in the market currently is the X1 160 Pro. However, it does not fit our design nozzle height. It could print smaller versions, as its build volume is 800 by 500 by 400 millimeters, and therefore a custom printer will need to be commissioned for this company in order to create something that will have the same print quality and is capable of printing that required material. The reason we want to use X1 system is due to their triple ACT system, which delivers industry-leading part density and repeatability. It is able to print at speeds topping 10,000 centimeters an hour, and you can see pictured in the top right is an example of experimental thrusters being created by Velo 3D, and note the very complex geometry that they are able to achieve while using binder jetting but with Inconel. Binder jetting has various steps that include preparation of the raw material, binder jetting itself, curing, debinding, and post-processing. Current limitations for manufacturing times include 1 hour for a bed-sized square meter to produce a 1 centimeter thickness, meaning a rocket of a height 2.16 meters can take roughly 216 hours, or if it's on its side with a diameter of 1 meter, it could take 100 hours to print. Only one part or nozzle can be printed at once due to its large size. No stackability is possible due to the geometry of the nozzle. However, you could potentially split the nozzle into two, but this defeats the purpose of creating a single component. No supports are required to be designed or implemented due to the binder jetting method. Each layer is supported by the powder bed, and this means complex inner geometries can be made without having to worry about creating internal supports or removing internal supports. Instead, internal channels will be filled with powder and will require cleaning out. These can be removed by either compressed air, vacuum, or brushes to remove the powder on the green body. Note that this must be done carefully, as it is the weakest point of the component and must be treated delicately. In terms of print orientation, the XY plane should have the largest cross-sectional area of the part, and the maximum dimension orientation of this plane should be parallel to the moving orientation of the print head. This can facilitate an increase in mechanical strength, especially for ceramic parts. This is due to more binder being able to attach to the powdered material as seen in the first image. Note also that the surfaces that require a lower surface roughness should be parallel to the XY plane, and therefore there is going to be a trade-off, and typically strength is going to be preferred. Surfaces, especially with bevels, have a greater surface roughness due to the step effects, which are difficult to avoid. Therefore, in order to optimize the printing of the OPRA nozzle, the largest cross-section would be to lay the nozzle on its side when printing. This orientation also limits the angle of the bevels or steps, thereby also improving the print quality. Either orientation will produce similar times, and therefore keeping structural integrity and surface finish a priority is ideal. The initial finish will not be sufficient for our application. The powder bed fusion method will always have relative porosity and a rough surface. Depowdering is the first stage in the post-processing, where the green body is covered in the powder once the print is completed. This green body is very weak, and therefore delicate depowdering is required. This process will directly affect the surface roughness. Other dry depowdering methods include blowing air, vibration, and vacuuming. The next step in post-processing would be densification. In order to make the final piece have the required mechanical properties, various densification methods can be used. Sintering is contacting the particles to bond at high temperature that occurs by solid-state diffusion at a temperature below the melting point. The driving force of sintering is the reduction of the total interfacial energy of the compacted powder, and prolonged sintering allows for grain growth and thereby an increase in the mechanical properties as shown in the image on the top left. Infiltration can also be done. It should not be necessary due to the high resolution and print quality and the material selection. However, to achieve near full density, infiltration could be used if compositional changes do not affect the part performance and an introduction of a new element does not deteriorate the mechanical properties of our part. In the future, there have been advances that could include the following methods, but they are still under experimental testing to determine their effectiveness versus sintering. Since sintering is the most common process and more readily available, it is what will be used. These future advances include CVI, which is chemical vapor infiltration, and PIP, which is pyrolysis. The next stage in the post-processing is external finishing. We have selected micro-shot peening, and it is used to deburr and smooth the outer surface of the nozzle. This is preferred as it is less aggressive than shot peening, and in order to then obtain the best possible finishing, some filing and sanding can also be done to achieve that mirror-like finish. Internal finishing will use the AFM, abrasive flow machining method. This allows us to smooth the internal cooling channels, and this is done by using an abrasive liquid being forced back and forth through these internal channels until the desired roughness is achieved. This system will also...
Going to the economic analysis section, the one-part rocket assembly production details can be divided into several sections. In general, we estimated the cost of one unit built is around $568,000, and this is only the cost of production just for the rocket nozzle. We estimated initial cost for the binder jetting 3D printer is cost around $500,000, and the raw material going to be cost around $300 per kilogram. Based on the specification of the printer, the total hours to print one single part using the binder jetting 3D printer to be roughly around 216 hours per unit built. This is because the speed of the printer can print 1 centimeter of height per hour. As a result, it took 216 hours to completely print the whole rocket nozzle. Also, an additional 34 hours is required for the post-process after the part being printed, such as to clean the part, cure it with selective heat treatment, and also surface finish treatment. We will go in depth for the total cost estimation in the next slide. Going into each section of production cost, an average price of binder jetting 3D printer machine is between $250,000 to $500,000 Canadian dollar for industrial purpose. Until now, no other company manufactured 3D printer that can fit with our design. Therefore, our estimation is based on the largest binder jetting 3D printer machine today, made by X1 company, which has the capacity of 160 liter in volume, and the machine is called X1 160 Pro. For the operating cost, taking account all of the utilities consumed, floor space cost in making one product at a time, we estimated the total of operation is roughly $1,000 per hour. Adding the number up with the total hours for one product, from printing the parts to post-process, the total cost per build is going to be around 250,000 Canadian dollar per unit built. For the material cost, using zirconium carbide powder that costs 200 Canadian dollar per kilogram, and the binder liquid agent, polyethylene wax, that costs roughly around $2.13 per kilogram. In total, the raw material is going to cost around $282.30 per kilogram. For the labor cost, assuming that they receive a minimum of $35 per hour, and for the labor cost, assuming that they receive a minimum wage of $35 per hour, the person will receive a total of 19,250 Canadian dollar per build if we calculate it by the hour they are working. With all of that, the total cost estimation per unit build is around 568,000 Canadian dollars in total. To answer the question whether zirconium carbide is recyclable, the answer is yes. However, as with many recycling schemes, the cost to produce a material by recycling waste or scrap must be equal to or less than the cost to produce the same material from its raw component. There is two ways of recycling zirconium carbide, which is by separation recycling and direct reuse recycling. Noted that it needs to be pre-processed in order to continue with the way of recycling zirconium carbide. For the pre-process to separation recycling is gravity separation, classification, and magnetic separation. Noted that many of carbide materials are magnetic, therefore it is not suitable as such in this case. For the direct reuse recycling, the pre-process include wash, specific gravity separation, hand sorting, and etching. After all the pre-processes and several other processes, at the end, the zirconium carbide will be grinded, resizing, blending it with another chemical in order to make it reusable for another product. For the business case, the proposed retail price, if there is any, is going to be around 1.6 million to 2.8 million Canadian dollar, including the rocket engine. In comparison with other manufacturing methods, the lowest cost to produce rocket nozzle is around 1 million USD, while we calculated an estimation of $568,000 to produce the one-part rocket assembly using the AM process. The benefit of using the AM process is significantly lower the cost and time of production, increase efficiency, and less waste of material used to build this product. With that being said, we need at least 4 rocket nozzles to be built in order to break even and also make a profit if we were to commercialize our product to the consumer. Going to the next slide of business model cases, here are the several cases that have been breakdown into. For example, the time to produce the product is significantly faster compared to traditional method, as it only involves a few steps in manufacturing compared to the traditional method. For the cost to build per unit is cheaper using an AM process compared to traditional manufacturing method, as it uses less machine, labor, and time to produce the product. For the environmental impact side, because we use less machine, less material, and less time to produce a product, it helps to reduce carbon footprints as well as being responsible because of using a recyclable material. Other cases such as material use, costing detail per unit, quality and quantity, customizability, improved function, and sustainability have given much more benefit by using AM process compared to traditional manufacturing method. In conclusion, one-part rocket assembly, known as OPRA, is viable for future reference as technology improves. This could mean that it's allowed for entire assembly by using AM processes, even though it increases cost, but it helps us to use a fewer component and material. Lastly, there is always a room for improvement in building this part. Not to mention, a new process might be more effective to build OPRA with the help of future technology advancement. That's all for now. Thank you for listening.